After using the leading power function to predict the end behavior of a polynomial graph, it is then time to determine the end behavior of the polynomial function. Now, in the interior of the polynomial function, the graph is going to be achieving its x-intercepts, possibly multiple x-intercepts, the y-intercept, and it can have different behavior at different x-intercepts. So here's just a random example of a polynomial function. In this section, we're going to examine the interior behavior. So we're going to be interested in locating the x-intercepts of the graph. Those are also called zeros of the polynomial function. And we're going to learn how to determine the behavior of the function at those x-intercepts. Does it cross through the x-intercept or does it bounce at the x-intercept? And then finally, we'll talk about turning points, where a function either has a minimum or a local maximum point. So let's get some terminology straight for the zeros of a polynomial function. A zero of a polynomial function f of x, p of x, is the solution to the equation p of x equals 0. Now, we saw this terminology when we solved higher degree polynomial equations in Unit 2. Now we're just working with two variable polynomial functions. A degree n polynomial function can have at most n zeros. So if I have a degree 2 polynomial, I'll look for 2 zeros. If I have degree 3, 3 zeros, etc. Remember, zeros can be rational, irrational, or imaginary. Now, if you look at this statement right here, p of x equal to 0, when we understand that p of x is the same thing as y, ultimately we have our y value set equal to 0 here. Remember, when you set a y value equal to 0, that locates an x-intercept. So there's a relationship between the 0 of a polynomial function and an x-intercept. The difference is in the terminology. So let's get our terminology straight. Note, the following statements are equivalent. X equals k is a real 0 of the polynomial function. Well, if k is a 0, then it must have come from the factor x minus k. Think about that. If I set that factor equal to 0 and solve for x, we get the 0 x equals k. Also, based on what we observed up here, the 0 is associated with an x-intercept. So I'm going to take my 0 and write it as an ordered pair with a y-coordinate of 0 to properly write the address of the x-intercept. So the zeros of the polynomial function coordinate with the x-intercepts of a polynomial function. And of course, this comes from setting our polynomial function equal to 0. That is, the function value is equal to 0. And as we learned from Unit 2, the remainder when dividing the polynomial p of x by x minus k is equal to 0. We saw that with our study of synthetic division. So let's begin by practicing finding the zeros of the polynomial function. So on example 3, find all zeros of the polynomial function and then express the x-intercepts as ordered pairs. To find the 0 of a polynomial function, we set the whole thing equal to 0. Now remember, this is a y over here, so technically we're setting y equal to 0, and when y is equal to 0, we're dealing with an x-intercept. So we need to solve this degree 3 polynomial equation. Because it's degree 3, I'm anticipating at most 3 zeros. Recall that we can solve a higher degree polynomial equation by factoring. So in this case, we have a greatest common factor of x. If we take that out, that leaves behind 2x squared plus 7x plus 3. We can break our trinomial down into two binomial factors. 2x plus 1 times x plus 3. Then we set each factor equal to 0, not forgetting that cute little monomial factor. So one of our zeros is 0. And we'll set our second factor equal to 0 and solve for x. Subtract 1 from both sides and divide both sides by 2. And then setting our third factor equal to 0 and solving for x, we get x equals negative 3. So we have 3 zeros as predicted for this third degree polynomial equation. In order from smallest to largest, they are negative 3, negative 1/2, and 0. Now, we're going to dress them up a little bit to turn them into x-intercepts. So the zeros are the x-coordinates of the x-intercepts of this polynomial graph. So our x-intercepts would be ordered pairs -3, 0, -1/2, 0, and 0, 0. So again, zeros and x-intercepts are related. The difference is how we notate them. Let's practice this again on example B. We have the function k of x equals x to the fourth minus 16. And our purpose is to find the zeros and x-intercepts of this polynomial function. So we set the whole thing equal to 0, and then we can attempt to factor it. Now remember, we are looking for at most 4 zeros. This is the difference of two squares, so we could factor it as x squared plus 4 times x squared minus 4. Now recall, the sum of two squares is not factorable over the real numbers, so I'm going to leave that one as a quadratic factor. But the second factor is again the difference of two squares. We can break that down as x plus 2 times x minus 2. So now we're going to set each factor equal to 0 and solve for x, including that quadratic factor. When we set that one equal to 0, we could easily solve it using our square root method. So isolate your x squared term, take the square root of both sides, and we'll come up with 2 imaginary zeros plus and minus 2i. Also notice from our second factor, we get the 0, -2, and from our third factor, we have the 0, 2. So putting this together in a formal list, we have our real zeros first, -2 and +2, and then our imaginary zeros, -2i and +2i. So we did obtain 4 zeros. However, the graph of this polynomial is only going to have 2 x-intercepts. Remember, real numbers only can be plotted in the real plane. So our imaginary zeros will not correspond to an x-intercept on the graph. The only 2 x-intercepts that this polynomial will have is -2, 0, and 2, 0. For our last example, we're dealing with a degree 3 polynomial, so we can anticipate at most 3 zeros. So when we set the polynomial equal to 0, we can begin factoring by extracting the greatest common factor, which is x. This leaves behind x squared minus 4x plus 1. Now, one of our zeros is x equals 0, and we set that little factor equal to 0, but our second trinomial here does not factor. So we'll just go ahead and set it equal to 0 and solve for x using our quadratic formula. So recall from our quadratic formula, x is equal to -b, that's -4, plus or minus the square root of b squared, make sure you get that negative in parentheses, minus 4 times a, which is 1, and c, which is 1, all divided by 2 times a, or 2 times 1. So simplifying, we have positive 4 plus or minus the square root of 16 minus 4 under the radical over 2. This is 4 plus or minus the square root of 12 over 2. So let's simplify the square root of 12. Let's think of that as the square root of 4 times 3, which we could separate as the square root of 4 times the square root of 3, or we'll just call it 2 square root of 3. So we end up with 4 plus or minus 2 square root of 3 divided by 2. Now, in order to cancel uniformly, I'm going to go ahead and split up that fraction with each term over the denominator and then reduce. So we end up with 2 plus or minus the square root of 3. So that's 2 real zeros included there. So making our list formal, we have 3 zeros in order from smallest to largest. That's 2 minus the square root of 3. Don't forget we got x equals 0 from our other factor, and 2 plus the square root of 3. All of those are real numbers, so this polynomial would have 3 x-intercepts. That would be 2 minus the square root of 3 and 0, the origin 0, 0, and 2 plus the square root of 3 and 0. Now, once we can predict the end behavior of a polynomial graph by looking at its leading power function and find the zeros or x-intercepts of the polynomial, then we can begin to sketch a pretty detailed graph. However, we need to be aware that the graph can exhibit different forms of behavior at the x-intercepts. In order to interpret this behavior, we're going to define something called multiplicity. Here's the definition. If x minus k to the mth power is a repeated factor of the polynomial function p of x, then k is a zero of multiplicity m. So what does that mean? Well, my zero here is k, and we're going to have this factor raised to a power. So for example, I might have the factor x minus 2 raised to the third power somewhere in my polynomial. Now, when I set this equal to 0, we can see the 0 of that factor would be x equal to 2. But technically, because that factor is raised to the third power, I've got 3 identical copies of the same factor, each containing the same 0. So we say that x equals 2 is a 0 of multiplicity 3. So the 0 comes from setting the factor equal to 0. The multiplicity is the exponent on that repeated factor. Now, it's important to be able to recognize multiplicity because this predicts the behavior of the polynomial at that intercept. At a 0 of even multiplicity, the graph bounces on the x-axis. So if we take a look at our example graph over here, the polynomial comes down, it touches the x-axis at -2, and then it turns around and goes the other way. We say that it is bouncing on the x-axis. The technical word there is that the polynomial is tangent to the x-axis, but you can see it kind of looks like a bouncing ball. So this is going to occur if that exponent up there is even. Now, at a 0 of odd multiplicity, the graph is going to cross. So notice at our other 2 x-intercepts, the graph actually passes through the x-intercept. So both of those would have odd multiplicity. So if we look at our example up here, since we had an odd exponent, we could see our graph would cross the x-axis at 2. Now, don't confuse this with what we learned in the previous video. We were talking about end behavior and whether or not the leading power function was of even or odd degree. And we use that to determine if the ends rise or fall. So if I'm talking about end behavior, I'm looking at the leading power function and predicting if the ends rise or fall. But if I'm looking at the power of a factor, that is multiplicity, we use the even or oddness of that exponent to determine if the graph bounces or crosses the x-axis. So make sure you distinguish those two skills. Let's clarify this with an example. Identify the zeros of the polynomial function p of x. Now notice our polynomial function is already factored. That's good news. This is a pretty big polynomial. And we're going to identify the zeros and their respective multiplicities. And then we'll use that to determine if the graph bounces or crosses at that 0. So remember, to find the zeros, we set each factor equal to 0 and solve for x. So if I set 4x equal to 0 and solve for x, we're going to get x equals 0. Notice the exponent on that factor is 1. That's an odd number. So we can predict that the graph is going to cross the x-axis at x equals 0. My second 0 is going to come from this factor. If we set that equal to 0 and solve for x, we would get x equals 2. The exponent on that factor is 2, so we say the 0, 2 has a multiplicity of 2. That's an even number, so we can anticipate the graph is going to bounce on the x-axis at x equals 2. So it's going to touch and turn or be tangent at x equals 2. Working our way to the next factor, the 0 of that factor is -1. The exponent indicates its multiplicity. So this is multiplicity 3. That's an odd number. So again, we can predict the polynomial is going to cross the x-axis at x equals -1. The next 0 comes from this factor. The 0 is -6. The exponent on that factor is 1. That's an odd number, so the polynomial will cross at that 0. And then finally, our last factor has a 0 of 3. The exponent gives me its multiplicity. And remember, even multiplicity tells us that the graph is going to bounce or be tangent to the x-axis at x equals 3. So now we can not only locate the zeros and x-intercepts, but we can also predict the specific behavior of the graph at each one of those zeros. The last part of interior behavior that we need to be able to identify is the turning points. Between the x-intercepts of a polynomial graph, the function hits peaks and valleys, generally called turning points. And more specifically, they're called relative maxima and minima. That's how you'll learn them in Calculus 1. Now, a degree n polynomial, now remember, a degree n polynomial can have at most n zeros, but in between those zeros, we can have at most n minus 1 turning points. Let's look at a couple of example graphs to solidify that information. On example 5, use the x-intercepts and turning points to determine the minimum possible degree for each function. And then write a possible function that would fit the graph. So a possible function doesn't have to be unique. So clearly we're dealing with a polynomial function here because it's smooth and continuous. There's no sharp turns, cusps, or breaks. And the degree of the polynomial function is related to the number of x-intercepts and turning points the polynomial has. So in this case, we have 1, 2, 3, 4, 5 x-intercepts. And for the turning points, remember that's the peaks and valleys. We have a relative maximum here, a relative minimum here, a relative maximum here, and a relative minimum here. We have 4 turning points. Now remember, a degree n polynomial can have at most n minus 1 turning points. So we can determine that this polynomial must be degree 5. Now another thing that helps me to make that call is to observe that the polynomial crosses through the x-axis on each one of those green x-intercepts. That means they all have odd multiplicity. That means nobody counts twice. So we can confidently say this is a degree 5 polynomial function. Now, let's see if we can write a polynomial that would describe this curve. So I'm going to start with my leftmost x-intercept, which is -4. If -4 is the 0, it must have come from the factor x plus 4. Moving on to the next one. The 0 there is -2, so it came from the factor x plus 2. The next x-intercept there is x equals 0. That came from the factor x minus 0. We can just call that x. The 0, 2 corresponds to the factor x minus 2, and the 0, 4 would correspond to the factor x minus 4. The last thing that I want to observe is that the left end falls and the right side rises. So this matches the same pattern as our basic cubic power function with a positive leading coefficient. So we know this polynomial also has a positive leading coefficient. Now, I'm not going to take the time to multiply that out, but if you did, you would find out it is a degree 5 polynomial. Let's look at the next example. So the degree is based on the number of intercepts and turning points. So in this case, we have 1, 2, 3 intercepts. And we have a relative maximum and a relative minimum here. Oh, but there's a relative maximum there. Oh, forgot this one, relative minimum. So we have 1, 2, 3, 4 turning points. Now, at first, that seems to be a little bit of a contradiction, because if we look at our rule, a degree n polynomial can have at most n minus 1 turning points. So the number of turning points is less than the degree of the polynomial. But in this case, we have 3 intercepts and 4 turning points. So what we have to consider is the behavior of the polynomial at each x-intercept. Notice on this first one, the polynomial bounces on the x-axis. So we know this one must have at least multiplicity of 2. It has to have even multiplicity. It could be multiplicity of 4, but we're looking for the minimum possible degree. This one crosses the x-axis, so it's going to have odd multiplicity, or multiplicity of 1. And again, this one bounces on the x-axis, so I would anticipate multiplicity of 2. So with multiplicity considered, this would have degree 2 on its factor, degree 1, and degree 2. So 2 plus 2 plus 1 gives me degree 5. Now our polynomial fits the rule, because we have degree 5 with 1 less than that for the number of turning points. Keep the behavior of the polynomial of those x-intercepts in mind as we write the equation of its function. So starting with our first x-intercept, the 0 there is negative 2. That means it came from a factor x plus 2. But remember, it has to have at least multiplicity 2, so we're going to square that factor. The second 0 there is x equals 0. It's crossing the x-axis, so we'll assume that it has the minimum odd multiplicity, which is 1. And then finally, at x equals 3, we have the factor x minus 3, and it must have even multiplicity, again, because the graph is bouncing there. The last thing I want to think about is end behavior. Notice the left end rises and the right end falls. Recall that our basic cubic polynomial has this pattern, but if I multiply it by a negative, it's going to have this pattern. So we can tell this polynomial is going to have a negative leading coefficient. So there is a possible equation for that polynomial function. So interior behavior consists of finding x-intercepts, keeping the multiplicity of those intercepts in mind when we graph the function, as well as turning points.